Hi everyone. So today we are talking about precision and accuracy in measurements. All right. So we're taking measurements in the science lab, and we want to figure out if our measurements are precise and accurate. And a lot of times, just in our culture, people maybe equate precision with accuracy. Especially in science, they're not the same. Okay. So we're going to take a look at what the difference is. So precision is a measure of how similar a series of measurements are to each other, right? So it doesn't matter at all how close they are to maybe the target that we're looking for. It matters how similar they are to each other. So if we're looking at this target here, right? If I shoot 4 arrows and they all lie on the outside of the target, but close to each other, right? They're all close. These are precise shots, right? They're very close to each other. If I'm looking at chemistry, right, so at measurements in a lab, I know that the boiling point of water is 100 degrees Celsius. If I go to the lab and I take my own measurements, experimental measurements, and I come up with the following: 89.1, 89.1, 89.2 degrees Celsius, 88.9 degrees Celsius, 89.0, and 89.1. All of these are very similar to each other, right? All of these measurements. My highest measurement here is 89.2. My lowest measurement here is 88.9, right? So that's only a difference of 0.3 degrees Celsius. These are all very similar, right? The best way to figure out how precise measurements are is to actually find the range, just like I just did. You're going to take the highest, or the greatest number, minus the smallest, all right? The absolute value of that, right? So, granted, it will be positive anyway. 89.2 degrees C minus 88.9 degrees C, right? That would give me 0.3 degrees C, right? That's a very small measurement, right? These are all very close to each other, so these are precise. If we're looking at the actual value for the boiling point of water, 100 degrees Celsius. These are not relatively close to 100 degrees Celsius. So they are precise, they're close to each other, but they are not accurate. Because accuracy is a measure of how similar measurements are, our measurement is, to the real, true, or accepted measurement value. All right, the real, true, or accepted measurement value. So again, if we're looking at our target, when you have a target, right, the target that we're aiming for is this bullseye, right? That is the center of the target. That's what we're aiming for, is this bullseye. So if I shoot 4 arrows and they all lie within this bullseye region, those 4 shots are very accurate, right? They all went to the target. Coincidentally, since they're all near each other, they're also very precise, right? So in this example, we have measurements that are very accurate and very precise. If we're looking again at science, we have the boiling point of isopropyl alcohol, 6 degrees Celsius. If I go into the lab again and I take measurements, and I get measurements of 82.6 degrees Celsius, 82.6, 82.5, 82.7, 82.7, 82.6, all right? My accepted value is 82.6 degrees Celsius. I can tell just by looking at all of these values that they're very close to 82.6 degrees Celsius. All right? To actually figure out a little bit more legitimately, we can actually find the average here. Right? So if we're going to find the average, we're going to add all 6 of these together. Right? And when we add all 6 of them together, we would get 495.7 degrees Celsius, right? And we're going to divide that by the total number of measurements, which is 6. When you do this, you actually get an average of 82.6 degrees Celsius. My average is right on target. It is right where the accepted value for the boiling point of isopropyl alcohol is. So these are very accurate. If we look at them, they're all very similar to each other. They're all very precise as well, right? Now, since we're talking about accuracy, One of the big things that we do in chemistry is to calculate our percent error, because in all of our labs and in really all the measurements that we take, we want to figure out how accurate our measurements are. And a way to do that is to calculate the percent error. Now, percent error is the ratio of error in a measurement to an accepted value, okay? So when we're calculating percent error, here's our formula. We have an observed value, which is what we calculate, minus the accepted value, divided by the accepted value, and times 100. We're multiplying by 100 because we want to turn this into a percent. That is why the 100 is here. Now, what do the terms observed and accepted mean? Accepted value is a quantity used by general agreement of the scientific community, right? So the boiling point of water being 100 degrees Celsius, that is general agreement of the scientific community that that is the boiling point of water. Many experiments have been done on this. Scientists across the world have tested that, and that is our general agreement for the boiling point of water. Okay, so this accepted value, when we're thinking about it in maybe simpler terms, this is the measurement value that you're supposed to get in the lab. All right, the measurement value you're supposed to get. Whereas the observed value, which we sometimes call the experimental value, it's the value we get in an experiment, right? A quantitative value measured during an experiment, okay? So when we go into the lab, whatever value we get, this is the measurement value that we actually got. The accepted is what you're supposed to get, observed is what you got, okay? Now we can use all of this to actually calculate our percent error. When we're calculating percent error in science, ideally we want a small percent error, right? What a small percent error means when we do this calculation is that our measurements are accurate, right? The smaller the percent error, the more accurate our measurements are. In this example, we can calculate our percent error. An experiment performed to determine the density of lead yields a value of 10.95 grams per centimeters cubed. The accepted value for the density of lead is 11.342 grams per centimeters cubed. Find the percent error. This is typical of what we would do at the end of a lab. Here's our formula again, okay? So when I'm reading this, what I want to be looking at is where is my accepted value and where is my observed value. So an experiment to determine the density of lead yields a value of this. This is what my experiment yields. That's my observed, my O. Find the value for, or the accepted value for the density of lead is 11.342. This is the accepted value. It says right here, the accepted value. That's my A, okay? So I'm going to plug this into my equation. The observed, 10.95, here, 10.95 grams per centimeters cubed, minus the accepted, which is 11.342. So I plug in, minus 11.342 grams per centimeters cubed, divided by the accepted. I plug that accepted value in at the bottom too in my denominator. Notice that I'm using units the entire time. I am not just plugging in numbers, right? We are using units to show what our unit is in the end, all right? If we have grams per centimeters cubed divided by grams per centimeters cubed, ultimately, they're going to be gone. When we multiply by 100, our unit now becomes the percent, right? So when I do all of this math, I get a value, percent error value of negative 3.456%. Now, oftentimes people will say you should take the absolute value of the percent error, which you can, but whether it's negative or positive tells us good information that I actually want you guys to know. So here, if you have a negative percent error, that means that your value is lower than the accepted. So I know that my percent error is negative here. That means that the value that we measured is lower than the accepted, which we can see, right? A positive percent error means the value is greater than the accepted value, okay? One thing to note, we just learned about significant figures, right? My answer here, negative 3.456%, needs to reflect correct significant figures. And when we're dealing with percent error, because this is something we will see all year, you want to make sure that when you're looking at significant figures, you're looking at that measurement that you took. Remember that significant figures is all about the measurements that we're taking. This is the measurement that we took in the lab. This is the observed value. You should be looking at significant figures of this value, right? So this has 4 significant figures. My answer has 4 significant figures.